Hello, AP Calculus BC. You guys have survived our topic 4, and we're actually into our last unit of study before the AP exam. How exciting. Of course, there's a bunch of review. I mean, we have to review all of AB and all of BC to make sure you're fully prepared. But if you've been keeping up with your work, you should be feeling pretty darn good. This last topic is pretty short too. In fact, there's only 2 new days worth of material. But to build up to those, we're actually going to spend a decent amount of time reviewing some important material from AB. And we're going to start with the idea of linearization. So, what is linearization? Well, one of the most commonly asked questions on a free response, I can almost guarantee that it will show up somewhere, maybe on a multiple choice, is you're going to be given the growth rate, which is just a fancy, you see rate, so it's just a fancy way to say the first derivative of an equation. And then given just a point on the original curve, you're going to be asked to find additional values on that original curve. This is really laying the groundwork for everything we're going to do in topic 5, differential equations that you've seen before, and logistic differential equations, usually just shortened to logistic equations. How do we know? Let's see, I guess a better way to put this. We already know several ways to accomplish the idea of a linear approximation. Most commonly, if this is a linear approximation, you write a tangent line. And for values very close to that point of tangency, we're going to hope that the tangent line gives us an answer that's approximately equal to the original function. So just a quick, nice little graph of what the heck is going on here. All right, so we're going to be given something like, okay, we know that on the original graph, we'll say y is some function of x. So we have x, we have y. And we know on the original graph, there's the point 2, 5. Very exciting. Great. But that's the only thing we know about the original graph. We don't know if it's linear, quadratic, exponential, some combination. But lucky us, we also know the value of the derivative. We know that the derivative's equation is, I don't know, e to the x times natural log of x. Something random. Sure, sounds like fun. Okay, well, how does that help us? Well, using just these 2 pieces of information, the point and the slope, we're going to be able to create a tangent line that passes through this point. Okay, well, how does that work? Well, if we substitute in 2 to our tangent line, let's say that we're able to build a tangent line that looks, I don't know, something like this. Again, I'm making this up. This could be not accurate at all, but here is my tangent line. And then they're going to say, great, so you may not know what the original graph looks like. We'll do the original graph in red, but we do know what our tangent line looks like. We'll call this t of x. So now, instead of using the original equation, what if I use the tangent line to find the output of 2.1? Well, of course, based on our tangent line, the output of 2.1 is right here. And then the question becomes, is that a good approximation for the original graph? Well, if I sketched in my original graph that I, again, making up, looks something like this, and we compared the value of 2.1 on the original graph to the value we found on the tangent line, are those, quote, pretty close, end quote? Well, and I guess pretty close is kind of a matter of opinion here. You could say, well, yeah, visually those are pretty close, so I'm not too sad by the fact that maybe these are off by some amount. But then if you're like an engineer building something, you're like, I can't have that level of tolerance. If I'm off by more than 0.0001, my building falls down. Well, that would probably not be great. So again, it comes down to how much tolerance are you willing to accept? But the idea again here is that a tangent line can offer a nice approximation of a value on a function if you don't know anything else about the function besides its rate of change. So let's put this into action. We have a model of bacterial growth, P of t. P of t represents the population. It's known that P of 10 equals 5,000. And in general, the rate of growth in the population follows the rule P prime of t equals 0.02 P of t. Use a linear approximation about t equals 10 to approximate P of 10.5. All right, well, let's see what we can do. we are going to start with our tangent line. That doesn't seem too bad, right? It's about t equals 10, so I'm not going to call my tangent line t in this case because t is the input variable. So I don't know, let's just call it f of x. Why not? Or f of t. So f of t will be found by how? Well, we need to find the derivative at 10. That's p prime in this case. So p prime of 10 times t minus 10 plus p of 10. Can we find each of those pieces? Well, I hope so. We know already that, oops, r, p and r, same letter, I guess, that p of 10 is 5,000. That was given to us. That's pretty easy. And then to find p prime of 10, we have an equation for that, so we should probably use the equation. Struggling with my apostrophes today. There we go. So it's found by 0.02 times p of 10. But we can continue this out because we actually know p of 10. P of 10 is 5,000. And then 0.02, well, if you read that decimal correctly, we have 2 tenths. This is 2 100ths. And that allows us to simplify, right? Chop off a 0, another 0. It's just 2 times 50, that's 100. So our final tangent line here becomes 100 times t minus 10 plus 5,000. Great. We now have a tangent line. And so even though we don't have the graph of the original function, we have a graph of the tangent, we can go through and we can use the graph of the tangent, or the tangent line, to approximate the original function's value when you input 10.5. How do we do that? Well, we say that p of 10.5 is going to be approximated by the value of f of 10.5. Okay, so continuing this out here, f of 10.5 is found by doing, or evaluating our tangent line at 10.5. Simplifying this down, let's do a little mental math here. 10.5 minus 10 is 0.5, or 1/2. Half of 100 is 50. And so we end up with 5050. 5050. Interpret your answer using correct units. It's a little bit difficult here because we don't have too many units, I don't think, but we could say something like this. At t equals 10.5, the population of the bacterium is 50/50. Great. Now, this is using a tangent line. If you go back to our Taylor series, our topic 3 here, the whole point of using a Taylor series is that it's going to be more accurate than a tangent line. One of the issues of using a Taylor series, though, is you generally need more than one derivative, right? A Taylor series is accurate to a first derivative, but then also a second, and then a third, and so on and so forth. And you could start taking derivatives here, but I think you'd run into a point where eventually you just wouldn't be able to use the equation anymore. You wouldn't know enough values. So, oftentimes, we don't have enough information, so we just stick with this linearization idea. All right? The rest of today is really just getting some more practice in, and you should probably just work through the rest of this video without listening to me talk. There's, about 2.5 pages, give or take, but I will work through this, so if you do want to unpause, you can listen. Because most of these are problems 6 or 4 or 5, right? These are no calculator. The only one that is calculator active says so. You will need a graphing calculator for that one. Okay, so good luck, and if you need any help, you can unpause and check it out. All right, so here's our first one, equation of a line tangent at x equals 1. So we have f prime of 1 times x minus 1, and I always write this first just to kind of help me out. I think it gives a nice little guide, right? F prime of 1 is 5, and this is really nice with the table, right? F of 1 is -4. So our tangent line then is 5 times x minus 1 minus 4. And then they ask us to approximate the value of f of 1.2. We do want to be pretty careful with this in that we want to use that approximately. We don't want to say f of 1.2 equals. We are just approximating. It could be equal, but it probably isn't. Okay, t of 1.2, and then we continue down. Now, because this isn't calculator active, you can be very clever here, and you can just say, great, I'm done, right? This is acceptable on the AP exam because the right side of that approximately is a value. Now you could find the value if you want, but you really don't need to, and I'm not going to here. Is this approximation greater than or less than the actual value? When you're dealing with tangent lines, there's going to be some other piece of information in the problem that you haven't used yet, and in this case, it's the fact that we know the second derivative tells us f double prime is greater than 0. Now I'm going to write this conclusion slightly incorrectly, but we should probably see what the conclusion is first. So if we're told that f double prime of x is greater than 0, what does f of x look like? Well, that means f of x is concave up, so I always just sketch a parabola. It doesn't have to look like a parabola, but that's a nice example of a graph that's concave up everywhere. Then I just sketch out a tangent line. Doesn't matter where. No matter what, you'll notice that two corresponding points corresponding vertically, the tangent line's point is always lower or less than the point on the graph of f. Maybe I'll label this as f. And so we can have our conclusion here. The tangent line is going to be less than, which means the tangent line is an under approximation. So our conclusion, the approximation, abbreviate to your heart's content, is less than the actual value of f of 1.2 because f of x is concave up. All right. Now I did say I'd make a mistake here. Can you spot the mistake? And it's a little subtle. The mistake here is I said f of x is concave up. But as a reader, if I'm going through and I'm looking at this, I would say, well, wait, how does the student know f is concave up? Maybe their teacher just taught them that they just draw a concave up graph and they should just write that. Where in the problem did it tell them that? Oh, this guy right here, reference the material that's in the problem. So if you want to say f of x is concave up, you can, but ultimately we would want to say this. So because f double prime of x is greater than 0, which means f is concave up. And that would be fine. But really, the graders are just looking for this part right here. That is what causes our tangent line to be an under approximation. If you want to connect it to the fact that f is concave up, then fine, go for it. But don't skip this piece. That was given to you, and you can't just make the jump to something else without explaining how you got there. All right, moving on. The infamous potato problem. This was the most memed problem of 2017 for sure. So at a time of 0, a boiled potato is taken from, or apparently it forms a pot, that's very exciting, from a pot on a stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees Celsius. That is quite hot, right? 100 degrees is boiling in Celsius at time t equals 0. And the internal temperature of the potato is greater than 27 degrees for all times t greater than 0. And I always ask my students, any idea why the potato's temperature will always stay greater than 27? And those students, generally the ones in chemistry, usually get it. They're like, wait, isn't 27 degrees Celsius approximately room temperature? Yeah, that's pretty close to what I think a lot of experiments use as room temperature. So if the potato is 91 degrees, it's not going to fall under room temperature. It's not going to suck out of the warmth out of the room, all of the warmth out of the room, and cool down past that. So 27 degrees is really the floor for as much as it'll cool. The internal temperature of the potato at time t minutes can be modeled by the function h, which satisfies the differential equation given over there. H is measured in Celsius. H of 0 equals 91. One of the most important things that my students miss here is what are 0 and what are 91 measuring? And to me, it's all about going back to the definition. 0 is a t value, and 91 is an h value, right? We know that because they tell us that up above. All right, write an equation for the line tangent to the graph of h, blah, blah, blah. Use this equation to approximate the internal temperature at a time t equals 3. Okay, well, we got this. So we need a tangent line. We're not going to use t because that's already in here, so we'll just use f for our tangent line. So we'll say something like f of x equals, our slope, we have a slope equation here, is going to be dh dt evaluated at t equals 0 times t minus 0 plus h of 0. And that looks pretty good because we have this t minus 0 over here. We know h of 0, we were given that's 91. This should be f of t. I'm not quite sure why I put x there, sorry. But then we have an issue. How do we find dh dt at t equals 0? Here's dh dt, but it doesn't use t as an input. And we definitely don't want to replace h with 0, because if you replace h with 0, then you get a dh dt, a temperature that ends up being a negative times a negative, which means we have a positive change in temperature. That would be a really confusing potato if all of a sudden it decided to increase its temperature. I think our dh dt values better be negative here. So what do? Well, we need to remember that dh dt is actually a function of h. So even though it is at t equals 0, maybe another way to think of it is it's dh dt evaluated when t is 0 and when h is 91. And so when we look at this equation, really we want to replace h with 91. I'm going to do a little quick math up above. Negative 1/4 times 91 minus 27. Just working over, negative 1/4. This is not calculator active, so it is probably a good idea. Now, do you have to find this value? No, you could use this as your slope, but having done this problem a few times, you do actually need that later. So let's go ahead and just work it out. To get to 1, you do 4 and 7, that's 11. And then 2 plus 7 is 9, but I think we have to carry that 1 to get 64. And so I think that gives us negative 16. That is a much more respectable slope value here. It shows us that the temperature is decreasing. Great. Use this equation to approximate the internal temperature at T equals 3. Okay, so h of 3 is going to be approximated by f of 3. So h of 3 is going to be approximated by f of 3, negative 16 times 3 plus 91, and great. There we go. I'm so proud of us. If you wanted to continue this out, I would probably stop here on a free response. No reason to make extra mistakes. You can. This is negative 48 plus 91. Continuing this over, it looks like it's going to be 43. Should probably double check that math since I'm not using a calculator, but that seems fine. 43 degrees Celsius. All right, part B. Use the second derivative to determine whether your answer in part A is an under or overestimate at t equals 3. Okay, well, let's find the second derivative first, right? So we are going to start with this guy up here, dh dt. But having done this problem several times, I found students find it easier when they distribute the negative 1/4. So let's do negative 1/4 h plus 27/4. And the question becomes, how do we take this guy and turn it into the second derivative? Well, it looks like there's an extra d in the numerator, right? D times d gets us d squared. And then dt, really we need to remember this is dt squared. So it's d dt of this side and d dt of the other side. What does that give us? Well, we get the second derivative of h with respect to t equals negative 1/4 is multiplying, that doesn't change. What's the derivative of h with respect to t? Certainly not 1, isn't that dh dt? And then the derivative of 27/4 with respect to any variable is 0, so I don't even need to write it. Okay. In fact, I should probably even go a little bit further here. Let's simplify this guy down because we know dh dt. dh dt is this guy up here. Or if you want, it's this one over here. Totally up to you. I'll use the original one, I think, though. Negative 1/4 h minus 27. Let's continue this guy out. Maybe I should have done that up above. Sorry. Save some room here. So we have negative 1/4 times, now I'm replacing dh dt with negative 1/4 h minus 27. Distributing the negative 1/4, I'm looking at 1/16 of h minus 27. All right. Well, how does the second derivative help us? Well, like we saw before, it's going to tell us about concavity of our function. Okay, if the second derivative is positive, our function's concave up under approximation. If the second derivative is negative, concave down over approximation. Well, how do we tell? Well, think about the values of h. Clearly, if h is larger than 12, if h is 27, this becomes 0. If h is 28, we get positive quantities. I think anything bigger than 27 will cause the second derivative to stay positive. And anything less than 27 will cause the second derivative to become negative. Do we know anything about h? Oh, didn't they tell us the internal temperature of the potato is always greater than 27? So we know that H is greater than 27. Okay, so as H is greater than 27 degrees Celsius, right? Then d2H over dt squared is greater than 0, and so the tangent, let's see, greater than 0. So concave up, tangent under approximates the true value. Nice. And I apologize for the lack of space. I was trying not to take up too many pieces of paper here. So we're doing okay. All right, let's look at our next one. Given the differential equation below, differential blah, 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 write an equation for the line tangent at x equals 2, approximate from there. You guys can do this one. Just don't forget when you do the tangent line, you substitute 2 in for x and 3 in for y. You don't need me. You can check my answers. All right. Grass clippings problem. Grass clippings are placed in a bin where they decompose. For 0 to 30, the amount of grass clippings remaining in the bin is modeled by A of t, where A of t is measured in pounds and t is measured in days. So we're going 30 days in a bin decomposition. For t greater than 30, L of t, the linear approximation, is a better model for the amount of grass clippings remaining in the bin. Use L of t to predict the time at which there will be 0.5 pounds of grass clippings remaining. Let's talk about grass clippings. Grass clippings is definitely going to be the output. Oops, measured. That's exciting. And let's see. So we are looking for predicting the time. We want to solve for t. Let's start with the linear approximation. Okay, because this is t, I'm not going to call this t of x. We'll go with f of t here. So f of t is going to be found, right? Oh no, wait, they called it L of t, didn't they? Let's just use their name. Duh. L of t, the linear approximation, okay, is going to be found by using a prime of, let's see, at 30 they told us, times t minus 30 plus a of 30. Okay, now let's start filling these things in. So we have L of t equals, we need to find a prime of 30 and a of 30, but luckily we have an equation a that's going to find a of 30, and it's also going to find a prime of 30 for us. That's very exciting. How is it going to do that? We have a calculator. I'm certainly not going to plug 30 into that and try to do it by hand. That sounds terrible. So as soon as I saw this problem, just kind of behind the scenes, I went through and I put this into my graphing screen. So if I jump over here, you'll notice 6.687, 0.931 to the, and I went to the x power because this is f of x. And I don't really care about the graph. You can hit enter though, and you see the graph hanging out over there. What I most care about now is that this equation is called f1 of x. So I'm going to jump back over to my other screen, and we're just going to find each of these values. Let's find f1, right, of 30. Great, so that's going to be our first one, 0.782. Okay, so we have plus 0.782, okay? And then we also need our slope. So our slope here is just the derivative at 30, and luckily our calculator can tackle that as well. Calculus derivative at a point, and we need to go through and substitute in 30 of what equation? Oh, it's called f1 of x. Great. And that is right there, negative 0.055. Awesome. Now what are we doing from here? Well, we need to predict the time at which there will be 0.5 pounds of grass clippings remaining. Okay, so do we substitute 0.5 in for time? No, because then there would be no time left. We want to find the time. So this is our output, which means we need to take this equation and we need to say, okay, where is 0.5 equal to negative 0.055 times t minus 30 plus 0.782? And although you could solve by hand, and there's nothing too bad about that, right? You subtract, divide, do all sorts of fun things. You could also graph to determine where these cross. Totally up to you. I'll do the old solve by hand thing, but because we have a graphing calculator, I'm going to try to keep everything together. So what does this look like? It's going to be 0.5 minus 0.782 divided by negative 0.055 is equal to t minus 30. See how I did both those at the same time? And then we just need to add 30 over. So it's going to be, and I'm just going to be extremely lazy here, add on 30. Now, let's do it all in the calculator. We're going to do 30 plus, and then we're going to do the fraction that I saw before, 0.5 minus what? Well, I don't actually want to type in 0.782. I want to type in the most accurate thing that I can, and that is up here. So I'm going to go up to that, hit enter, and it's going to paste it right down for me. And you can do that on the 84 as well. See how much more accurate that's going to be? And then divided by what? Divided by negative 0.055, that guy up there. Okay, so we're going to go up here. Oops, that's not what I wanted at all. We're going to go, there we go. And we're going to paste that guy in, but I really didn't want to do that. So instead, we're going to go up here, and we're going to do Control and then C. We're going to copy that guy. We'll go back down, and then Control V and paste it in. There we go. Now we're nice and accurate, and we're going to hit enter. 35.0544. We can get more decimals. 35.054 sounds pretty good to me. T equals 35.054. And notice that this is in days. It's good that we got a number larger than 30 because it says for t equals 30. And there we go. All right, last page here. We're done with the calculator for today, so you can put that away, and we'll jump on to 2015, number 4. Consider this differential equation. Write an equation for the line of the tangent. You can do that. And then find the second derivative. You can do that as well. However, C is where things get interesting. Y equals f of x has an initial condition given by f of 1 equals 2. Does f have a relative min, max, or neither at x equals 1? Well, you need to remember that in order to be a relative min or a relative max, that this needs to be a critical point. And what has to happen at a critical point? Well, the first derivative, in this case dy dx, either has to be 0 or does not exist at that point. So to check to see if this is a relative min or max, we should probably start by figuring out if this causes our derivative to be equal to 0. Okay, so let's check that. So dy dx equals, and we have x is 1 and y is 2, so 2 times 1 minus 2, yeah, that is 0. Okay, so we know that this is a critical point. That's great. But how do we narrow this down to see if it's a relative min or relative max? Well, normally you'd make a sign chart. But in order to do a sign chart, you'd have to be able to substitute in an x value and get an answer, or a y value and get an answer. But the only point that we know in this case is 1, 2. Okay? Notice it's a different initial condition than up there, so we can't use that same one. So what do we do here? We need to fall back on the very seldom remembered second derivative test. So I might as well actually find the second derivative up here, and that way you can test yourself and see if you found it correctly. We had to do d dx of each side. Okay. d dx of 2x is 2, and of y is dy dx. Going out further, because it said in terms of x and y, dy dx was 2x minus y, and finishing this off, 2 minus 2x plus y. All right. Well, what do we know about the point 1, 2? 1, 2. In particular, we know the slope is 0. So the graph is going to come down and it's going to flatten out like that. That'd be a relative min. Or the graph is going to come up, flatten down like that, could be a relative max. Or it could go up and look something like that, and then it's a neither. One way we can check this is by evaluating your critical point into the second derivative. So let's go ahead and find the second derivative evaluated at the point 1, 2. We're using this guy, 2 minus 2 by 1 plus 2. Okay, 2 minus 2 is 0, plus 2 is 2. We have a positive second derivative. What does that mean about the critical point? Well, it means at the time the graph meets the critical point, it is concave up. right? Has to be concave up there. And if you're concave up at a critical point, that critical point has to be a relative min. So how do we conclude here? We would say f has a relative min because the first derivative at 1, 2 equals 0 and the second derivative at 1, 2 is positive. You could say equals 2 if you wanted. That is the second derivative test. The second derivative test tests to ensure the point is a critical point, and then make sure that your second derivative is positive or negative. By the way, if the second derivative was equal to 0 there, it would be inconclusive and you'd have to find a different way to do it. All right. This last problem is so similar to everything we've done that I think I'm going to leave that as an exercise to you guys. I used to hate that when my professors would say it in college. This is left as an exercise to the reader. However, I have posted all my solutions to this on Teams, so you can always check those if you would like. Thank you for hanging out with me and remembering some linearization, the idea that very, very close to a point of tangency, both the tangent line and the original graph look linear, and the tangent line will give a value that is very similar to an unknown graph. I'm excited to have you guys back next class where we can start reviewing some of our differential equation knowledge.